So let's have a look at the two-scale approach. But let's use a slightly different way of doing things. Let's look at it using the product rule. So this is non-examinable. It's just looking at the two-scale method from a slightly different perspective. Just see if that helps you understand what's going on. So let's take a typical differential equation. So d2y dt squared plus epsilon dy dt plus y equals 0 with initial conditions y equals 1, dy dt equals 0 at t equals 0. And the kind of solution we're anticipating for an equation like this, so we're expecting it could be an exponential envelope. So slow decay of amplitude. And fast oscillations. So with the context of two-scale method, the standard approach is to say, let's take y of t, and it says substitute in y of t in tau, where tau is epsilon times t. Okay, we're going to do the same thing here, but we're going to make an assumption. So we're going to assume that we can write y of t in tau as a product. So we're going to say it's a product of u of tau and v of t. So this won't work for all two-scale problems, which is why it's not part of the standard method, but it will work for this problem. So it's worth looking at this just to see how the two-scale method works for a slightly different point of view. So we want to substitute this new form of capital Y of t into our differential equation. So the first thing we need is to work out what the derivatives look like in this new form. So dy dt, that's d dt of u of tau v of t. So we're going to use the product rule and the chain rule. So first off, product rule, so that's going to be u dv dt plus v, and then du dt, we're going to use a chain rule to work that out. So that's du d tau dt, and d tau dt is going to be epsilon. So dy dt, that's going to be u dv dt plus epsilon du d tau times v. Okay, I also need a second derivative. So I'm just going to differentiate this thing again. Two terms, and I'm going to apply the product rule to each term. So d2y y dt squared. So first off, first term. So that's going to be u d2v dt squared. And then I'm going to differentiate u, but as before, I'm going to use a chain rule. So that's going to give me epsilon du d tau. So all this is du dt, which is du d tau dt, and d tau dt is epsilon. So that's first term done. Oh, nope, sorry. I need dv dt here. Then differentiate the second term. So plus epsilon du d tau. Leave this term alone. Let's tidy that up. D tau, and now dv dt. And then I'm going to differentiate the first term twice. So that's going to give me epsilon squared du d2u d tau squared times v. And I can combine these two terms. So d2y dt squared, that's going to be u d2v dt squared plus 2 epsilon du d tau dv dt plus epsilon squared d2u d tau squared times v.